All right, good morning. How you guys doing? Apparently I need some help speaking. Well, just like my voice, myself in general, my lecture, I'm feeling a little less prepared than normal, so I apologize for that. But we are going to talk about, kind of wrap up a little bit of the discussion on generating these pH versus log concentration plots. A couple last notes on that leads us into titration. We'll talk about that. I hope that it'll be enough to get you to the point where you can complete the homework, but it might not be. So do your best and use this as a moment to say, okay, well, this is the direction it's pointing, and then you can see what you can do, and I'm going to be lenient on if I didn't cover enough of that. And then I'll do my best to clear that up and clarify that on Thursday. So that'll be today. So we'll probably touch on titration a bit more Thursday as we go over the homework. And as I consider that, we should then have an exam next week, I believe, right? Pull up the syllabus for us. Okay, so I need to update the topics here. So we're going to get to dissolved CO2 chemistry after the exam. Might have to speed things along a little bit, but basically our homework covers kind of most everything up till this point, including the titration that we're going to talk about today, and that means our exam will kind of similarly cover up to that point as well. So I do need to move these topics further. Of course, we already have some understanding of the carbonate system as we've covered, but we haven't gone in depth on that. Okay, so that's kind of where we're at. Time is flying. All right, any questions or concerns before we get going? All right. Okay, so last time we talked about these log concentration plots versus pH. Talked about the HA case and the NA case, where we were looking at kind of what is this equivalence point, where does that show up, how do we draw these things, and what kind of utility can we get from drawing them. There's one more case to talk about, and that's when it's not just HA or NAA, rather what happens if we're adding something else to change the pH. Because if we just had NAA, that was kind of what we were looking at. If we just added NAA, we could reach the NAA equivalence point. We could also use it if we had HA and added enough base to get there. Or if we just had HA, likewise, we could get to the HA equivalent point or add enough acid to get there. But what happens if we're adding some of both, right? What happens if we're adjusting the pH to try to go somewhere else that is not that equivalence point? And I think I have, let me check real quick. I think I have a little reminder. The equivalence points that we were talking about were showing up here and here, where the amount of HA or NAA, I guess HA or A minus really, in solution crossed the amount of OH minus or H plus. That's how we were describing these equivalence points. So considering that, coming back a step, if we wanted to work with a solution where we're not aiming for a pH right at either of those points, then we have some mixture of acids and bases, not just the HA or NAA. Okay, so in order to work with that kind of situation, we can again come to the electroneutrality equation, and that's kind of where we're going to develop this concept from. So we want to change the pH, but we don't want to change the concentration of our particular acid A. So that's the key. So maybe our HA is acetic acid, and then we're going to add hydrochloric acid as a way to change the pH without changing the total amount of acetic acid in solution. So that's the concept here, where we don't want to change acid A. So instead, so let's say, imagine A is acetic acid. So we can have a constant amount of that particular acid, constant total amount, and then add HCl to lower the pH, for example. Okay, so then we're going to assume that as we're adjusting the pH, we're using a strong acid or a strong base like NaCl or NaOH. There's a few others that could serve there. Potassium hydroxide, for example, KOH could work just fine too. So in this case, our electroneutrality equation, if we put the positives on the left, negatives on the right, we would have H plus Na plus on the left, and then A minus, OH minus, and Cl minus on the right. What we can find here is that the amount of Na plus in this system should exactly trace the amount of base that we add. Now that's going to be true of the amount of strong base that we add, Cb. That's going to be true even if we didn't add NaOH, even if it's all coming from the fact that maybe we added NaA. And the reason this is going to hold true is when we kind of take a look at all this, there's that counterbalancing effect where if we add NaA, then it's going to have the same amount of basic conditions as if we added HA and an equivalent amount of NaOH to get to whatever pH that we happen to be at. So it's kind of interesting. It might not be exactly intuitive at first, but the Na plus, the sodium, traces our base, and conversely, the Cl minus is going to trace our acid, as if we were adding HCl. That's coming out of this electroneutrality equation. So we can take our electroneutrality equation and rearrange it then if we take that to be the case and substitute, instead of Na plus, we're going to put in the concentration of our strong base here. Likewise, we can take the concentration of our strong acid as Ca and sub that in for the Cl minus spot. So just simply rearranging this equation and adding in our alpha fraction A1 times A total, so this total amount of, in our example, acetic acid, times the fraction that is the A minus version of that. That gives us that term. And so we can have a new equation here, and what we're looking for, as we'll see in the next slide, is some net amount of base that we add, the concentration of base compared to the acid. So that's kind of where we're heading with this, this discussion. This concept, the net strong base concept, is really, and we could do net strong acid. It's very much the same thing in reverse. But the net strong base is a very common way to look at our systems, and it's very common to titrate systems by adding strong base and measuring, okay, how much did we add and what impact did that have on our system. So the Cb minus Ca is our definition for a net strong base. So this net could be negative, right? We have a net negative strong base, meaning we had added a strong acid. Okay, so it's not necessarily meaning that we've added base, because in net it could be negative. But we use it in this manner because usually we're adding base. So if we had no no base added and just some acid, yeah, that's negative. But in general, it could be 0, the net strong base, it could be positive or negative. And we can set, based on the previous equation, we can rearrange this equation, subtract H plus from both sides, and subtract that concentration of the strong acid from both sides. And we get that equation, right? So that's our net strong base equation in terms that are relatively convenient, right? We have this alpha fraction, which we know is typically a equilibrium constant, and pH is what affects that. The total amount of that acid that we were interested in, that we also didn't want to change, right? That was AT. We're shifting the pH without changing that. And then it's just OH minus and H plus. Okay, so that means just by understanding the pH and given some total amount of acid in solution, or some species like that, could be a strong acid, weak acid, could be a base. I guess we'd write it as a B there, but you get the point. Just by then understanding the pH and the equilibrium constant that we might need, we can have a relationship between the net strong base and that AT. So this is how the titration becomes useful. There's going to be some relationship between this net strong base term and a total. So that gives us a way that we might be able to measure a total by measuring the net strong base required to have some pH outcome. That's kind of where this is heading. Okay, so to go a little further to define this net strong base term, the Cb minus Ca, if we are at the NaA equivalence point, which is over here, if you recall, then our net strong base is positive. That by definition we have added base to get there compared to our starting point, which we will define as the net strong base being 0 when we are at the HA equivalence point, right here. And if we take a moment to look at that equation, Cb minus Ca, for that to be 0, find my cursor, for this to be 0, the right side obviously has to be 0. So we could either have at pH 7, these two would cancel and this guy would have to be 0. So our alpha fraction would have to be approximately 0. Or more likely, we're going to have some A minus, because that's essentially what we're talking about here. And that's going to be counterbalanced by acid, right? So if we have some A minus in solution and some OH minus, is always going to be some, then what we notice is to get those three terms to combine to 0, we have to be slightly acidic at least, right? So if, the only other alternative is that maybe this is A minus is so close to 0 that we're at a neutral pH. As soon as we're at a basic pH, the equation can't get to 0. Can never be it. So in that sense, if the left side is 0, the right side, or pH 7 is the very maximum we could ever be. So that's why this is going to push our net strong base to be 0 or less, or to B0 at a acidic condition, which also makes sense just by saying that, right? Net strong base. If there's no net strong base, we're not in a basic condition. So when I say it that way, it becomes a little more self-evident, I suppose. Okay, below that HA equivalence point, then our NSB is a negative number, or we could call it a net strong acid at that point. Okay, so likewise we could define, so just as we define net strong base as Cb minus Ca, we could define a net strong acid as Ca minus Cb. Would rearrange the equation a bit, but it would be no problem. And that also means the net strong base is equal to the negative net strong acid. I don't think people use net strong acid too much, but it's just clear that that could be used if you wanted to, right? And I think it's mostly just convention because it tends to be more convenient to do titrations with base. Okay. So just putting this graph up here a little bigger, and this is a couple other notes on it for us to take a look at. So if we have Cb minus Ca is less than 0, we are on the left side of this HA equivalence point. If we are adding HCl, we're heading in this direction. If we're adding NaOH, heading to the right, and that'll move us across these places. And remember that the HA and A minus, we're on a log concentration plot. We could say log C, well, I guess it's also including the OH and stuff. But this is a log concentration plot where the total amount of A is approximately 10 to the minus third moles per liter. Okay. So as we consider this net strong base calculation, one thing that we have to kind of grapple with is, okay, what are the units here? Do they make sense? How does this really sort with the electroneutrality equation? So Cb minus Ca feels like it should be units of a base and units of concentration, right? Moles per liter. However, we're using this in the context of the electroneutrality equation. So what we can see is, well, on the left-hand side, we could also write that as one equivalent positive charge per mole of H plus times the H plus concentration. I guess this is on the left side before we rearranged to get this equation. So when this was still over here. And likewise, the Na plus is one positive charge per mole Na, and so on. So we could sort it out and say, okay, well, these are technically just net equivalent charges per, so moles of equivalent charge per liter, essentially, or charge equivalents per liter. All of that can sort out to make sense for what we have as these the left side. Now, the remaining pieces on the right side are slightly different, especially if we go to a more complicated system, because they are essentially the if we take the Na plus and things like that to the left side, those are spectator ions. They're not going to be doing anything. If we put the Cl minus as our acid tracer and the Na plus as our base tracer, so if we do Na plus and anything like it, and Cl minus and anything like it, as the left-hand side, those units are clearly and easily become that strong base or strong acid per liter, and the equivalent charge. But on the right-hand side, then we're dealing with something that's slightly different, because those are kind of defined as capable of taking a proton. But we can get to the same charge equivalence from from that perspective that they are non-spectator, meaning they are engaged in consuming or producing protons. And so we can get to that same concept there. So when we have a slightly more complicated system, like let's say groundwater with some CO2 in it, we can think about it in terms of, okay, what's the spectators, what are the non-spectators? So if we just start with the electroneutrality equation for this groundwater, it's got sodium, chloride, calcium, and CO2. So on the left-hand side, we'll start with the cations and then the anions on the right, and then we're going to rearrange it. So we had H+, Na+, and because we're doing the charge, we have 2 charges per calcium multiplied by the calcium concentration, right? And on the right side, we have bicarbonate, 2 times the carbonate, same reason, OH minus and Cl minus. So we can rearrange this into the same format. So we're going to go from this to the Cb minus Ca equals the other stuff, right? And so doing that, what I'm really saying is that we're going to get the spectator ions on the left, these ones that trace the amount of acid and base that we've added. So in this case, the net strong base is traced by the sodium and this calcium, but see, we have 2 of them. And you can visualize this very easily if you imagine what would a calcium base look like. So calcium is 2+, and OH minus would be the base, and you'd have to have 2 of them in order to satisfy that molecule. So if we had calcium hydroxide, it would be CaOH2, so you get 2 OHs, OH minuses, for every 1 calcium. So that's why the it could be very intuitive to say this is going to count twice for the system here. Okay. It also follows because of the charge. We are dealing with electroneutrality here. So that's the way you can think about it. Then minus the Cl minus, that's going to be the left-hand side. On the right-hand side, we've subtracted the H+, and we have all these species. Now, each of these can and will be involved with consuming acid, right? So if we were to adjust the pH by adding acid, this HCO3 minus can consume 1 proton. So this would be 1 H+, and it would yield H2CO3, right? And this CO3 2 minus could consume 2 protons to get to H2CO3. OH minus could consume a proton to get to H2O. And H plus can consume, we'll just say 1 H plus here. And 1 H plus would cancel out with a negative H plus, right? So in that sense, on the right-hand side, what we're doing is we're counting how many protons would it take to get that term to be a net neutral, I suppose. This is the way to look at it. How many protons can each of those consume? And so this definition, really tying back to where we started, shows us in large part why these spectator ones trace the amount of strong base or acid that we add. They serve as a very convenient tracer. Okay. All right, make sense? Okay. So bringing this just a little further, one thing to see is that if we were to add sodium chloride, which seems like we're going to throw everything off, in this case, neither the sodium or the chloride have any impact on H+. They're both spectators. And so they're not actually going to change the Cb minus Ca calculation because that calculation would have the Na plus minus the Cl minus. You could even do the same thing for calcium chloride, CaCl2. You'd be adding the Cl, be adding for every one Cl, you'd be at Ca, you'd be adding 2 Cls. So we can see that's not going to have a direct impact on this net strong base calculation. Okay, and in fact, we have the electron neutrality equation, you know, the cations equal to the anions. That's true, and that relates directly here, but it's so common to use this formulation, the spectator ions versus the non-spectator ions, that we often simply write it this way. And in fact, it's essentially the equation for alkalinity is the same thing. So you'll see it quite often. It is derived directly from the electron neutrality equation, slightly adapted, I guess. Okay, we could take a look at some examples. There's a couple here that may be worth your time to come back to and look at. So I'll read through it. We're not going to solve it right now, but this one says we can, you know, for calculating pH and the net strong base, so Cb minus Ca from an acid base alpha value. So for the system, and I don't think I brought that figure with us. Okay, so there's a figure and it shows associated with this particular Ka, particular acid concentration, some strong base is added to the solution at the HA equivalence point. The value of alpha 0 is lowered to 0.3, assuming standard temperature pressure. Activity is neglected. What is the pH? And how many equivalents of strong base per liter are needed to accomplish this change? Okay, so of course we would need the figure as well, but that's something that we can take a look at, is what happens if we adjust that alpha value to a particular spot. How much acid did it take to get there, and what would that process look like? Another would be to calculate that net strong base required given some pH and total acid. So again, using that same same case, we consider a solution that is at a pH of 10, and the question is, okay, the first question is, what is the initial net strong base for that condition? Then in part B, how much net strong base needs to be added per liter to lower the pH to 3? And so net strong base to lower it should be a negative number, right? So part B should be negative, whatever else. Yeah. Okay. So maybe worth taking a look at those, and I'll try to add that figure here so we can take a look at it to have it in the notes. So. Okay, so I want to move on though to talk a bit about titrations. And okay, what exactly is titration and how might we go about using them? So, a titration. You've done them before, pretty sure, in general chemistry lab, if not high school chem or something like that. Essentially, we're adding a small bit of a concentrated acid or base and observing the pH change when we do. And we're going to do this until we see something interesting happen. A lot of times it would have been a big color change or something like that, and then we know visibly that, something happened, right? And if you recall, almost always when you're doing that, you probably have a special dripper. There's a it's a volumetric something, right? Forget what it's called exactly. Probably with a little knob. And it's going to have all these gradations for you to see, okay, how much, what's your concentration, or excuse me, what's your volume that you've added, where did you start, and then you're dripping it one by one, and you get the before and after to get the volume of your titrant that you add. And the reason for that is because you want a small amount of liquid dripping into a larger volume, so that you're not having a big change in volume for your overall solution, because you don't want to change your AT. So AT should be approximately constant. Technically, you are diluting it when you're adding your titrant, but if we take 100 milliliters and we're only dripping like half a milliliter or less at a time, every drop we can change the amount of acid or base quite a lot, and we're only having a point something percent impact on the AT concentration. So you could even do this in, let's say, half a liter, and then even if you're doing 1 milliliter every drop, which would be a very large drop, that's still less than a percentage of your volume, right? So we want AT to effectively be constant, at least for the purposes of our study. And we can add a base that would be alkalimetric titration, or an acidometric titration. It's going to be a strong acid or a strong base in either case. And it's usually going to be quite concentrated, something like 0.1 normal. As you do a titration experiment, you could plot it something like this, where we have how much have we added on the x-axis, and tracking the pH on the y. So this would be adding more of our base or acid, in this case base, and then we would expect the pH to rise as we go forward. If we were adding an acid, of course, it would probably look different, kind of reverse. So it's at least for me, probably I'm guessing for some of you also, we've looked at a lot of diagrams that are pH on the x-axis. So once we stop and look at this, we have to, take a moment to readjust our expectations that, okay, the pH is now on the y-axis, right? So if we've added some particular amount of base, then we hit this big change, we know something happened in the chemistry, right? Now, as soon as we're adding a small amount of acid, we have a big change in pH. So the system is sensitive to the pH at that spot. Whereas in some cases, it's not so sensitive. Okay, given that we have on this x-axis the amount of base added, and it is a strong base, we can kind of see then, we can say this in terms of what we were just describing, this net strong base, right? So instead of, we can use CB minus CA instead of this, instead of NaOH added. So we can replace that x-axis with specifically net strong base, which is kind of convenient, because then all the stuff we just talked about with the equations and electroneutrality stuff then plugs straight into our plot. And it's like, oh, okay, here's this plot, so we should be able to read something about, if CB minus CA is 0, at some point we could mark it 0 here, and we have a negative and a positive. That can clue us into what it looks like in terms of where we're at with the equivalence points or some things like that. Okay, so we talked about the titration in practice a bit. We often will use titration to determine alkalinity or a specific buffering capacity. If you've ever done any pH chemistry with the lab, if you're using pure water and just adding a strong base or acid, it's hard to control that pH, right? It's going to go all over the place. So we add a buffer to slow it down in certain regions. There will be times when it's, regions where it's hard to get anything close, but there's going to be other regions where it is buffered nicely, where you can accidentally add a lot of acid or base and it doesn't really change the pH too much. Okay, a couple general considerations, or kind of a few thoughts, a couple case scenarios. When we write it, just recall that when we're writing this as Cb minus Ca, the net strong base, this would be kind of the format. The portion that is A minus, or the amount of A minus really, plus OH minus minus H plus. It's kind of the generic form for HA. And we can consider two limiting cases for an HA system. And what I'm gonna do is I'm gonna talk about these cases here. And at this point, I was getting a bit frustrated with our book. And so we'll talk about this, and then I switched over to the other book, which is a little more practical and straightforward, I think. This one was taking a little too much time to get there. But we'll take a look at these cases, and then we're going to take a look at an example from the other book on, okay, well, how do we use that to, like I said earlier, calculate some concentration of AT? Okay, case one, we have an extremely strong acid, HA. Maybe that's HCl. That means the Ka value is very large, or the pKa is perhaps a negative number. Okay, and alpha 1, that means would be 0 throughout the titration. So meaning no matter where we are within the titration, it's almost all in the A minus form. So again, if we had HCl as our HA, across all ranges of pH, HCl in water is going to be just Cl minus, and the H plus is gone, right? So that's an extremely strong acid. Okay, so that would be kind of an example for case one. All right, so under that condition, we can write our net strong base equation as Cb minus Ca is equal to A total plus OH minus minus H plus. And the reason we can say that is because we just assumed that alpha is approximately 1, right? Because we could keep the alpha 1 here, but we said it's equal to 1. And in this case, we said alpha 1. In the converse case, case 2, HA is extremely weak, and Ka is very small, and throughout our titration, wherever range we're covering, alpha 1 is approximately 0. So that means that maybe the pKa is so small that, or the Ka is so small that the pKa is, I don't know, pH 10 or something, and everything we're interested in, perhaps below that, it's pretty much all going to be in the HA form. Okay, that would be an exceedingly weak acid. That means our Cb minus Ca becomes simply OH minus minus H plus. Okay, when we plot these two, and then by the way, under this condition, when Cb minus Ca is 0, H plus is equal to OH minus, right? So that actually calls back to kind of what we were talking about earlier. So we can plot these two cases and see that we have, should be case 1 on the left, and case 2 on the right. I think. notice that the pH 7 occurs right here. And the question is, did I get this? Probably got that backwards. Because if this is defined here as the CB minus CA is 0, then this should be case 2. Apologies. Okay. Well, what we can see is when we plot these as how much base have we added before we get a change in pH, it's the same general shape. That shape is gonna come out for a monoprotic acid that we're using, but where that's occurring in terms of how much base we've added is different. Okay, and of course, if we're adding base, we're moving across this plot to the right. We could add acid and head on this plot to the left. Okay. There's a couple other terms that I think we will discuss next time, but like I said, I was getting a little frustrated with this book. This G and this F, we're going to come back to. They have some meaning that I'd like to get a better handle on before we discuss. Okay. The only other thing I want to point out right now is this kind of gray area in the middle for each of them. It's really demonstrating the area where we have rapid changes in pH for small changes in our titrant. Right, so those are kind of the really sensitive points of these two systems. Okay. So I'm going to move over to an example on ammonium. This is from the other book, and bear with me here. We're going to kind of read through it and process it step by step, because I think it's a pretty nice encapsulation of putting these pieces together, at least as best I could manage today. So if we have a titration curve, looks something like this for this ammonium example, where we can add more base, and I think we're starting with ammonium chloride, so NH4Cl. We don't know what concentration it is, so we're going to call this AT, and we're kind of not sure how much we have. But we can do our titration experiment and see how much base that we add in order to observe something that happens to the pH. So all we need is a known volume of base that we're going to add and a pH meter. Okay, with those two pieces of information, which are fairly easy compared to some other stuff, we're going to try to find that AT concentration. Okay, so we have 1 liter solution, unknown amount of ammonium in it. I guess they were probably meaning to say ammonium/ammonia. We can determine the concentration using the following procedure. First, we take 0.0 moles of strong acid. We add by introducing 5 mils of 2 molar HCl. So we basically we drop the pH first. We want to start at a low pH so that we can then add our base and measure from there, because we have to have a starting point. So we start at 0, or well, start at rather pH 2, and then we begin. So then we're adding, from this starting point, we start adding base. If we measure our CB minus CA, or we calculate that, we are starting at a kind of a negative spot. And recall that we can know that even if we don't know AT, because we can know on the left-hand side of our system, we said we can let's see. I guess this might not be added as ammonium chloride. Maybe we just don't even know. It's going to be some mixture of NH4 plus and NH3. I don't think we were given anything about how it was added. So then that means whatever acid we added, the HCl, we know the Cl concentration. So we can, let's see, on the left-hand side of the equation, it was what the Na plus minus the Cl minus, I think would be the total solution here for Cb minus Ca. Basically, we can know the Cb minus Ca without knowing the At. That's my point, right? And then we can be adding base, strong base, and we know, okay, we're incrementing based on the strong base that we're adding. Okay, so we started there. We begin to add NaOH, increments of 0.0025 moles. That would be 0.5 milliliter drops of a 5 molar solution. As long as the pH changes little, excuse me, we're adding that amount as long as it changes just a little bit. And then once it starts changing faster, we add smaller increments. So we drop it to 0.25 mils drops when it starts changing fast. And we slow it down a bit so that we can get a little bit of information between right here, basically, as much as possible, because it's so sensitive to the pH in that spot. Okay, so then we can know that resulting concentration like I talked about, and we can measure how much base did it require to go from one spot to the next. All right, so let me, so figure 7.2 here lists the value of Cb minus Ca, the resulting concentration of strong base added minus the resulting concentration of strong acid added. So we had already added the acid, so now we're just adding that strong base there. The resulting pH also shown, and a titration curve generated from these data is shown. The titration curve provides information about the system being titrated. There are 2 inflection points of the graph where the curvature changes from concave upward, so changes from looking like this to looking like this, right? So we have from concave upward to concave downward. There's 2 spots it does that. So it kind of does that twice, right? So we have right here, and then it rose up to here, and it started going this way, and then it did it again. If we take a close look, that's kind of what we see. So those 2 spots are interesting to us because they tell us about what's happening based on our conversation about these equivalence points. So these occur at the points where Cb minus Ca is equal to 0. That's right here, right? There's our 0. So that's our first equivalence point, because we said our HA equivalence point is when Cb minus Ca is 0. That's how we defined it for HA. So that's the first one. And if we start measuring from there to the next point, well, the next point, we might call these a pure conjugate acid endpoint and a pure conjugate base endpoint. That should be the NaA equivalence point at that point. Okay, so if we measure, it occurs there, and it occurs at 0.01 molar concentration added. The distance here between these inflection points gives us the total concentration of the weak acid base system present. So that gives us AT, is what it's saying, because that's the difference between the HA equivalence point and the NAA equivalence point. And if you recall, these equivalence points were the amount of acid you would have to add to get to HA if you started with completely NAA. That's how we defined the the HA equivalence point. And conversely, the NAA equivalence point was defined as the amount of base you'd have to add to get an equal amount, to get to that amount of A minus if you started with HA. So that difference there is the amount of weak acid in that solution. So I'm just going to say just a reminder or remember the equivalence point definitions. Okay, so then 0.01 moles per liter is that concentration. This is also true for polyprotic systems. So when we have more than one, more than just HA, maybe H2B or something like that, the distance between any two inflection points gives a concentration of the acid-base system present. And I think that would be two neighboring ones, I would expect. At CB minus CA equals 0, the pH equals that if we had added 0.01 moles per liter of NH4Cl to the water. That's this point right here. That's our HA equivalence point, also known as, or it says thus, this is the pure conjugate endpoint of the system. When 0.01 moles of base have been added to the system, CB minus CBA equals 0.01, the equivalence point is reached. This is the pure conjugate base endpoint. Okay, so that's going from on our graph that we had the H plus and OH minus, and we were looking at where these points were crossing to get the HA and the NAA equivalence points. This is that, that dynamic right there. Okay, does that make some sense? It's a little tricky, and like I said earlier, I wished I had a little more time to better prepare, but yeah, the two books combined, I hope that's a good point for the moment. That's all I have for you today. There is a bit more, so I will try to go through it, but I think and hope that can get you to the point where you'll get through the homework. Of course, you can also look at the books.
So for the titration curve on the homework, are we supposed to have the exact data points, or can we just draw a rough curve?
Probably just a rough curve. You could maybe use Excel to do something like that. I don't remember what the problem asks exactly.
It just gave us I think it's a solution of NaOCl that we're titrating with a strong acid.
Okay.
But we just have the AT value. And I don't know how to get any notation on that.
Okay, so yeah, let's take a quick look at this. So we have HOCl, the acidity constant, and we're saying that we can be determined by titration with a strong acid. So sketch a curve indicating pH at the beginning and the end point. I think there's a bit more material on how to sketch one of these curves, but I also don't think it would be too difficult to assemble that in Excel or even use your MATLAB code and put in the KA. So I'll leave it to you on how you want to approach it. Just make an informed effort. Is what I'll say. Is that fair?
So what specific criteria do you want on the graph? Do you want like the equivalent ones?
I think the graph we just looked at is probably a good, let's see, probably a good indication of what you ought to do, because it kind of gives some kind of endpoints, starting point and end point. So probably a little bit beyond that, just to kind of show what it's probably going to look like. And then, yeah, labeling the pieces. So something like this graph. Right. Any other questions? Issues? Okay. Well, I'll leave it off there then. I'll see you guys on Thursday.